You know, when you look at an old exam paper, what do you see? Just a test, right? Well, what if I told you it's actually something more? Like an instruction manual for the entire world around you. Today, we're going to take a standard physics exam and use it to unlock the science that's hiding in plain sight. Yeah, really. Tucked away inside these questions about circuits, energy, and gases are the fundamental rules of our reality. So let's use this physics paper as our map and take a little tour of the science we all experience every single day. So here's our game plan. We'll start with a simple flashlight, then we'll feel the forces at play on a water slide, we'll watch the science bubble away inside a kettle, and finally, we'll explore the invisible dance happening inside a party balloon. And trust me, you'll be surprised at how it's all connected. All right, you ready? Let's kick off our little test for reality and see what we can uncover. Let's begin with something you've probably got stashed in a drawer somewhere, a torch or a flashlight. In the real world, it's just a solid object. But in physics, we can translate it into this language of symbols and lines to see exactly how it works. So here you can see the real-world torch right next to its circuit diagram. You can think of that diagram as a kind of map. It strips away all the extra stuff, like the plastic casing, and shows us the exact path that electricity takes to make light. It's all about the function. So, what makes this the correct diagram? Well, the question in the source paper tells us it needs 3 cells, that's batteries, stacked up for power. It also has to have a switch, which is basically the drawbridge that opens or closes the path for the current. And most importantly, the LED has to be pointing the right way. See, an LED is like a one-way street for electricity. If you put it in backwards, the flow just stops completely. Nothing happens. Okay, so from that tiny flow of electrons in a torch, let's scale things way up to the massive rush of a person down a water slide. Now we're shifting our focus from electricity to energy and how it transforms from one form to another. And here we are, the Aqua chute. It looks like a whole lot of fun, doesn't it? But really, it's a giant open-air physics experiment. Every single person who goes down this slide is demonstrating a core principle of the universe, the conservation of energy. At the very top of the slide, a rider is full of what's called gravitational potential energy. It's basically stored up energy they have because of their height. The moment they push off, that stored energy starts converting into kinetic energy. That's the energy of motion. To put it simply, the higher you start, the faster you're going to go. And we can actually put some hard numbers on this. The exam paper tells us that a rider converts 8.33 kilojoules of potential energy as they drop 17 meters. This just goes to show that the energy isn't lost. It just transforms from that stored potential into the thrilling rush of speed. All right, from the very visible motion of a water slide, let's look at something a bit more subtle, the simple act of boiling water. How can we possibly see the physics at play here? Well, we have to look at the data. This graph right here from our exam paper tells the entire story of a kettle coming to a boil. Along the bottom, we've got time and seconds, and on the side, we've got temperature in degrees Celsius. It's basically the biography of your morning cup of tea. So let's follow the journey. For the first 15 seconds or so, not a whole lot happens. That's just the heating element itself getting hot. Then, from 15 to 90 seconds, you see this beautiful straight line going up. That's the element efficiently pouring energy into the water, raising its temperature at a really constant rate. But then, the curve flattens out right at 100 degrees. The kettle is still pumping in energy, but it's not raising the temperature anymore. Instead, it's using all that energy to turn the water into steam. For our final stop, let's go from things we can see and measure, like speed and temperature, to the invisible world that makes it all happen, the world of particles. So here it is, a simple party balloon. It holds its shape because there are billions and billions of helium gas particles trapped inside, all constantly moving and pushing against the inner surface. But what does that movement actually look like? Well, question 10.1 in our paper gives us a few options, and the reality is a beautiful kind of chaos. The particles are not moving in neat, predictable paths at all. Instead, they move in completely random directions, kind of like a swarm of bees in a box, and they do it with a whole range of different speeds. They're constantly colliding with each other and changing direction. So let's take this one step further. The paper asks what happens if you increase the temperature of the gas inside that balloon, assuming its volume stays the same. Why would the pressure go up? It's a perfect chain of cause and effect. First, you add heat, which is just a form of energy. That energy gets transferred to the helium particles, making them move faster.
Because they're speeding up, they collide with the walls of the balloon more often and with more force. And that combined increase in how often and how hard they hit the walls, well, that's exactly what we measure as an increase in pressure.
So there you have it. We've gone from a torch circuit to a water slide, from a boiling kettle to the invisible particles bouncing around in a balloon. And we did it all using just a single exam paper as our guide. And that's really the big takeaway here. These principles aren't just for exams. They're like the software that runs the hardware of our universe. They explain everything, from why a light turns on to why a balloon stays inflated. So the next time you switch on a light, just take a second. You're not just doing a simple task. You are interacting with the fundamental laws of the cosmos, which kind of makes you wonder, doesn't it? What else in your world is just waiting to be explained?